like round.
Yeah.
But he's like, you can't masturbate.
Right.
He's like, that's my thing. He's like, I gotta figure that one out.
We'll talk more later. Taylor Ann.
You'll see it.
What is that application for, by the way? So that's what specific applications for undergrad or for a program?
For a bachelor's degree.
So it's for actual.
I can bring
So it's an application for
when you have
application to undergrad.
I could do dance.
we take a
So then, yeah,
Oh,
to run a little
tank.
bit more than what they give or something like that. Okay. All right, I'll have that done. And then when you say your name, when you spell your name, you have to you say Taylor Ann or just Taylor? Officially. So it is, and that's a capital A.
Yeah.
Okay. No, that's okay. I just want to make sure as I'm putting it in, it's right and official so that they're looking at it and everything correlates. Otherwise, it's a problem. Okay. Okay, so let's get started. Let me see. Where did we end off? Reaction order right here? Is this where we were? We did this, I'm pretty sure, right? And we did this. We did this.
yeah, page 8. We're going on to page 9 now.
So the
Oh, sorry, like this one.
We're starting reaction order.
We basically
Here?
finished. Yeah, we finished the order.
okay, reaction order. That's this. And
Experimental determination.
we're right here.
Yeah.
This table here.
Yeah.
We didn't.
Yeah, we
didn't
didn't
go
go
over
over
it?
that.
What about this one?
Neither.
That's where we stopped right here.
Yeah.
Right. We didn't look
Okay.
at that. That was the.
Yeah, this we did because I wrote this on the board.
Yeah. You even wrote it on the board before we
Yeah,
even
so I
got
know
there.
we did this one.
Yeah.
Yeah.
But you're saying we didn't do anything else. Okay, so let's get so let's kind of backtrack and kind of collect ourselves where we're at. We've moved through fairly slow to make sure that everybody's on board. It's a new topic. We started off with rates, right? We looked at different rates based on a balanced chemical equation, right? In the balancing of that chemical equation, we saw that anything that was a reactant, we took the concentration of it divided by its concentration, or its coefficient in the balanced chemical equation, divided by the change in the time, right? So that's what a rate was.
Right.
And then if we looked at the product part of that, then it was positive. The reactant was negative. Okay. Then we progressed to rate laws, right? And rate law was what? How did we define rate law? Anybody? It was now the rate was relative to what? Concentration, right?
Yes.
And we started looking at how that what that looked like. What was a rate law? And we looked at the reactants, and that's where we were right now, going through rate laws, looking at the concentration of the reactants, which the rate equals that times K, and K was constant, right? That was the reaction constant. And there's a lot of things wrapped up in that constant that we're going to get to probably later this week or next week. So in that, then the challenge was, what is the order of the concentration within the rate law, right? And that's what we're looking at here, the reaction order. And how do we figure that out? Experimentally, right? So you either have to have data to figure it out, which have we covered any examples of that yet?
No.
We're still working our way to it. Or you can end up with an order. These are the different types of orders based on if you double the concentration, then you have the order of a particular reactant, and that dictates the rate of that reaction, right?
Right.
So let's take a look. We have a rate is equal to K times, let's say, reactant 1 and reactant 2, and the order is referenced here as either, let's say, M and N, and we determine that, and that's where we were at the moment. Okay? So if I double the concentration, double this, then what happens to the rate? If I double this, I look at the rate, so I double this, and I get 4 times the rate. I know I have a second order, and this M gets changed to 2. That's what this chart means. Okay. Okay. Now, So the key here is, what are we doing? At this point, we're just figuring out what these are. This is where we're at this point in the discussion for this chapter. Okay, so here we have the concentration. And by the way, at this point, we're going to start evaluating graphs in the context of figuring out a lot of stuff as well, up through the rate laws. Okay, and then after we get into K, we can still play with graphs. So we're now evaluating this part here. Then we're going to readjust this into what's called the integrated rate law, and then we're going to focus on K. That's the progression of this chapter. Okay, and in doing that, we're going to look at these things. So it's more quantitative. We're going to look at this both in the context of determining this based on data and also determining different things involved relative to graphs. So understanding the graph's important. So the first thing when you look at a graph, just to remind you, is you've got to know what the axes are, right? What is the y and the x-axis? In this case, we're looking at time relative to the concentration of A. A is going to be based on something that's related to just the decomposition, let's say, of A. So A breaks up into some two other things. So A is going to be the reactant. Okay, so we're looking at the concentration of the reactant relative to time here. As time goes on, what happens to the reactants? They decrease in concentration. That should make sense. That's what we're talking about in terms of rates, right? We're moving across a balanced chemical equation. So let's say A goes over to, let's say C plus D. Decomposition. So this is the A we're looking at. So the rate of this one would be K, A, and then we'd have to determine what goes here, because this coefficient, does that have anything to do with the order? No, absolutely not. So in the context of looking at this graph, this is what I'm interpreting. This is what this graph is relating to. So here, if I look at this line going straight down at the concentration of A, then I'm looking at zero order. If I look here, the red line is first order and blue is second order, which means that you can see that the concentration here isn't going to matter that much. It's not, as I increase or decrease the concentration to start with, it's not going to matter where I go along. But here, as I lose some of the concentration, and this one as well, what happens?
Slows down.
It starts to slow down. The rate starts to slow down. Absolutely. That's exactly what that means, right? Hence, correlating it to the previous slide, zero order, no effect on the rate. First and second order, the rate doubles or quadruples. So as I add more, that means over time, it's going to reduce. And that's what this chart is showing you. Okay. I will say that all of these are in the context of the same constant, which we have not unpacked yet, right? Which deals with activation rate we talked about, orientation, temperature, and a variety of other things that are not spoken. They're all wrapped up in this K, and we'll unpack that later. Okay, so that's assuming that the rate constant is the same. Okay. Now looking at another graph that's sort of representing the same thing in a different way is now I'm looking at the rate in molarity per second over the concentration of the reactant. Okay, and in this case, as you would expect, what happens at a zero order in terms of the rate?
Oh, nothing?
It's constant.
Right.
So that's what we see here. It doesn't matter. It stays constant all the way across. The rate never changes relative to the concentration of this. That's what that's showing. And then you can see that the first order to the first, it goes straight across. So as I double this, it doubles that, double, double, and it just keeps going up in that pattern. This one, slightly different. Second order is squared. So the rate quadruples per doubling the concentration of the reactant. And that's what this is representing there, that line. Okay.
So like mathematically, these lines would be the derivatives of the first ones, right? So the rates of how they change.
Going from this one, you're looking at this. This becomes this divided by this for the rate, right? And then this is this relative to just the concentration or the rate law, right? Because that's what we're assessing in the rate law is the rate relative to the concentration of the reactant. So this is representative more of the rate law. where the first one is representative of what? Just the rates. This divided by the time.
This graph is showing, doesn't matter as to what you're looking at, whether the reactant or the catalyst?
This is focused on the reactant, not the catalyst. But if I did put a catalyst in here, which I won't,
Right.
You can put it in there because it is going to be ordered.
Okay.
So for this graph, that would make sense. And for this graph as well, yes.
Okay.
You could think of the A as a potential catalyst, even though that's very rare.
Right.
Yes. Okay, now let's solve it, okay? Those charts are just for you to gauge what's happening. You're not going to get any information from those charts. When we get a little bit further and we get into the integrated rate laws, those charts you will specifically interpret some of the things in here. The charts I just showed you, those are just for intellectual understanding of what's happening if you pit them to each other. So you're not going to worry about getting too much information from those kinds of charts. Shorter expected reaction accounts must be found. We talked about this. Let's just do it. Let's do an example. So now we've built it up. You've been given the orders, you understand what the orders are, now you're going to solve for the orders. That's what these next series of examples are going to be. So here's some data, and here's you need to have, okay. One thing throughout the rest of this course, when you're looking at something, if you can, always try to put together the balanced chemical equation. For rates, it's going to help you understand what you're looking at, where things are, but it's also from here on out going to help you with any other thing that we do with equilibriums. Without knowing this, you can't really assess what it is you're trying to solve for. So unless it's given, then you can solve for this. And that's something you acquired from 101 in terms of your skill set and how to do things based on different things. So in this case, it's given. And you can see the initial reactant in molarity. In experiment 1 is this. Experiment 2 is this. The rate of disappearance of this is given right here. So with this concentration, I get this. With this concentration, I get this. And you notice there's only one reactant. Okay. If there were more than one reactant, then I would have to deal with that, and we'll discuss that in a little bit. For now, there's only one reactant, which makes this a little easier. Mm-hmm. So what happens when I go from experiment 1 to experiment 2? Doubles. So remember that earlier chart, what we started with, when something doubles, then we want to see what happens to the rate.
Right.
So what happens here?
Doubles.
It doubles, great. So I want to know the rate law, so I say the rate is equal to K, concentration of N2O5, and now I say from data, if this doubles and this doubles, what's my order of this?
First order?
First order, so it's just 1, so I leave it.
Right.
This is my rate law for this chemical reaction. Everybody see that? If this had quadrupled, what would I do here? Put a 2 there.
2, right.
And that's how you use the data to interpret the order of the reaction. But you have to do it for each reactant. In this case, there's only 1, which makes it easier. If I had 2 reactants or more, then I have to look at the data, and wherever I could find one of them doubling and the other staying constant, then I could assess what that effect is on the rate.
0.
If both of them change, then I can't use that data to assess it because I don't know which one's causing that change. Right? I could have one at 0 order and one at the second order, and it doubles. I won't know which one that is. So I have to hold one constant if I have more than one reactant, and I'll show you an example of that.
I was going to look at the initial and the rate, right? Both of them?
What's that?
They need to match the initial of the concentration of that and the rate of that same concentration of the same reactant. You have to look at both of the things there. You see how the initial actually doubled from experiment 1 to 2, and then also the rate also doubled. Can it be that the rate be different though?
He's asking, can the rate not double? Can it just?
What happens if the rate doesn't change?
No, if
It's 0 order.
oh, okay, so it's always going to
This
be
is
either
dictating the order referencing the exponent right here, m. Well, we just determined from this data when the concentration doubles, what happens to the rate. If the rate is 0, I should say, if the rate is the same, then this
that's
is
the
0
constant.
order.
Okay.
And this whole thing just becomes rate equals k, because that's 1.
Gotcha.
But because this doubled, then that means what?
That'll be the
The
second-
order
first
is
order, right.
1. So let me, just because I'm sure you're not the only one not sure, so let me do this. See this chart here? I doubled the concentration. What happened to the rate?
Oh, gotcha.
Doubled the concentration, the rate doubled, first order, this becomes 1. Does that help
Yes,
put everything
yes,
in
yes,
perspective, maybe?
Yeah.
So you see, that's why we spoke about the first thing first. I was building it up, and now I'm showing you how you actually determine it with data. But this is why you need that data.
Yes.
Does that make sense now?
Absolutely.
Okay, cool. That probably helped others, so definitely keep that in mind.
That's it.
So here we go, double.
Okay.
Whoops, what happened? Double, which makes it a first order. Is that what they're gonna tell us now? Oh, here we go. Oh, good, everything I just did is right here. This is real awkward. So, I don't like this. You saw how I used that chart?
Yeah.
Much cleaner.
Indeed.
I don't know why you would write all this stuff additionally, but there's your 2, so rate over 1, rate over 2 gives you 2. That makes the rate order 1, so 2 to the 1 is 2. Reaction is first order. Once again, just follow that little chart. Okay, no big deal. You can do all of this if you like, but it's not going to really, it's going to take longer. What I can say is,
If the numbers are not clear.
Does it
So-
become more complicated or it's better to use that?
no, not in my opinion.
Okay.
But it may be for somebody else, if you think slightly different than me, then use it that way. I think it's just added work, and then added work adds confusion, in my opinion. Okay. So, this is the same kind of thing we've already looked at, and I think I did this thing on the board last time. So this is, once again, you're just looking at what happens to the rate based on the change in the reaction, and that gives you the reaction order. And we've talked about all of that. The other chart's probably more useful, but this is just another way to view that other chart. What do I want to see here? What would be challenging? I'm showing you everything as though it doubled, right? But consider what would happen if you looked at something that tripled or quadrupled in terms of the concentration. Then what would you expect the rate to occur? And then you could look at a chart like this and see what happens. Okay? You're just tripling or quadrupling instead of doubling. So think about that. I'm not going to give you any examples in class. If I can put together some of those exit tickets that I know Carlos asked about. Did you get those, by the way? No, nothing was sent to you?
I sent an email.
Yeah, okay. I forwarded it to Saeed to try to get you those, so I'll double check on that. But I'll provide some exit tickets that might show you something and how to use this if you were tripling it, let's say. Okay. But for now, this is just the same kind of chart that you had before.
So to think about whether triples, quadruples on the rate.
Yeah, same thing here, right? Rate is quadrupled, reaction order is doubled.
All right.
That's if you double the concentration, of course.
Okay.
That's assuming all of these things are being doubled.
Right.
Is there a limit to the reaction order, or is there a range we're going to be doing?
Right here.
Okay.
Actually, the range would just be on the previous slide, because there I think we have a square root of 2,
Yeah.
which is the 1/2.
And the negative.
And then we have a -1, which is, what is that?
The negative is the 1/2 and the square root.
Yeah. And then the square, and the other one's
Is the
square root of
half.
2, so there are 5.
Yeah.
The main focus, okay, so there are 5 that you're introduced to. They don't always have to be, and I think I brought this up last time, but now I'm just reminding you, they don't always have to be whole numbers, right?
Right.
I think the square root of 2 is an example. Is that 1.4 or something like that, 1.41 or whatever? They could be something else as well. I won't give you anything outside of those ranges. What the main ones are 0, 1, and 2. We're going to focus on, and 0 is not that relevant a lot of times because it's just
Constant.
1, right? So it doesn't do anything. But reaction order 1 and 2 is what we're going to focus on, and we're going to look at those in the integrated rate laws and things like that. But if you were just asked for the rate law and to determine the order, then the other ones you could use for that. What?
Square root 2 is half.
The square root, if you take the reaction order of 1/2, so let's say this is A 1/2, that's the same thing as saying A 0.5, right? And if you had the let's say this is A minus 1, that's the same thing as saying 1 over the concentration of A.
Right.
Okay, two different things. Okay, so let's take a look at another example here. Okay, so here, this is a more difficult set of data, right? And what's going on here? How is this different than the last one? What part of the balanced chemical equation do you know based on what you have here?
There's a lot more reactants.
3 reactants, maybe one is a catalyst or not, but you know that these 3 things are all in the reactant side or a catalyst, okay? In other words, what are you looking at here? You need to look at this data and then say, what am I looking at? If I
Okay.
put up a, no, I don't put up, okay. I have 4 experiments here. If I want to find out what happens, what the reaction order of this is, what do I do? So I look at this 1 and 2 because this doubles, right?
Right.
But the rest have to stay constant, and they do. So if this doubles, what happened to this? If it doubles, what's the reaction order on that one?
1.
That's it. That's all you guys would have to do.
Cool. Let's take a
Right? That's pretty easy when it's put in this context, right? Well, what if I want to know I? I can go 1 and 3, I can go 2 and 3, I can go 3 and 4. What do I also need to make sure of?
Yeah, those are constant.
If I go 1 and 3, is that constant?
Yeah.
Is that constant?
Yes.
So then I look here, what happens from here to here?
Doubles.
Doubles. So it's also
1.
1. Now what about this one?
That's
If I go from
catalyst.
here to here, that stays the same and that stays the same. So if I go from here to here, what happens from here to here?
Constant.
It stays the same. So what order is it?
0.
0. So how do I write the rate law here then? From that, just from what we looked at, how do I write the rate law for this?
Okay. Equals H2O. H2O2. And then 1. Uh-huh.
Huh? So it just becomes 1,
Oh yeah, and you don't put the 1s there.
right? So
Uh-huh.
the H plus does, you can put a 1 there, but it doesn't,
Right.
right?
Cool.
Okay, so let's see if we're right.
1 and 4, right?
What's that?
We compared 1 and 4.
1 and 4, constant, constant, double. It's not always going to be that easy, obviously. You'll have to pick and choose which ones are right or wrong. It doesn't always have to be 1 to, et cetera. It could be 2 to 3, where the others are held constant. You'll have to figure that out, right? But ultimately, that's all you're doing.
It looked overwhelming. At
So let's take a look.
It looked overwhelming, but it was
No.
it's okay.
By the okay, here's another thing.
That's
From
our
this,
next experiment.
from this now, can I determine K?
Yeah.
Yeah, right? How?
Plug in the.
I can just plug in any one of these. It just has to be straight across, right?
Right.
So for H2O2, let's use this one. I put in 0.02. For I2, that'd be 0.01. For the rate, 2.3 times 10 to the minus 6. I take this, I divide by those, and I just solve for K.
Right.
K should be the same for all of them.
Right.
Hence, it's a constant. So you could solve for a little bit more with this as well.
Nice.
Okay, and that's all they're asking here. So we already determined the reaction orders with respect to each one, each reactant, potentially one of them was a catalyst, and then that's how you would solve for K.
So if you're determining the reaction order, you can just look at, for any reactant, any experiment, 1, 2, 3, 4, you just have to pick one. Whatever, 1 to 4, 2 to 3. like,
Whatever one
pick
doubles.
Doesn't, okay, so whatever one.
So the one you're looking at has to double or more, and the other ones, if there's more than one, remember the first example we only had one, so it didn't matter. But if there are any other ones, they have to stay constant. Because if they both move, then you don't know which one is causing that effect on the reaction, right? So you don't know which one's actually causing the effect on the rate. So everything must be constant, and then you look at the doubling of one thing, everything else constant, then you see what happens to the rate based on that. Now you know that that's specific to the rate. Yes. Yes, 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 yes.
Okay, so 0 doesn't have an effect on the rate, you just don't include it.
And if it becomes zero order, then it's just 1, right? Anything to the 0 order is 1. Okay. So here's the equation. These are all reactants, none of them are catalysts. And, okay, so we did this, doubled constant, doubled first order. Do it again, doubled constant, doubled first order. Doubled constant, constant, zero order. And we get first, zero. What's the overall, by the way? Just add them all together, right? It's not really that much useful information, but if you were asked that, you know it's 2. And then this is our, right here. So this drops off, that's just 1, and you usually don't include 1s above those. And there you go. So you guys figured it out pretty easy, right? And then the rate constant, let's just plug in one series of data from one experiment. We'll do it from the first one. Plug in, plug in. And we have this rate is here, divided by these two things over here. So that's 0.01 and 0.01. And that gives you 1.2 times 10 to the minus 2. And the K is going to be in 1 over molar and 1 over second. Okay, so I guess the key there is, how do we know that? From the units. How do we know what units those are? So that might be the only other thing that I haven't maybe touched on too much. If I have molar per second, and I have this over molar and molar, those cancel. This is over, so that's on the bottom. This is already on the bottom, so this is big M to the minus 1, it's on the bottom.
And then
S to the
is
minus 1, because it's also on the bottom.
Right.
And that's where the units are. Anybody not clear on that, how to work the units on that?
I might have accidentally,
What's that?
I might have accidentally times the mole by mole.
Over
And
here?
then you're left with 1 mole.
On the bottom you can, but then see, remember, 1 cancels with the top there.
Yeah.
No, but if you kind of do that first, you're stuck with 1 mole, and then if you cancel, then you're left with just
You
second.
don't treat it as mole squared.
Mole over mole squared,
Oh, okay. Yeah.
still the same thing. Doesn't matter. Okay, I think that covers everything I want you to know for this, so that you can solve something like this on an exam with the data. Oh, do I have another one? Okay, here's another one. We need to spend time, all right. So here, different experiments, A and B. So what are my reactants? A and B. Do I know anything about my products?
No.
Initial reaction rate. So let's determine, okay, first of all, let's assume they want us to write the rate law for this. So I know that the rate is going to be equal to K times the concentration of A, we'll put N there, times the concentration of B, and we'll put M there, okay? So the first thing is, I want to know what N and M are. Okay? If I keep this constant here, and B doubles, what happens to the initial rate?
Constant?
Constant, doesn't change.
Right.
So I know that B, M is 1, or 0.
Zero.
0, which means that that whole thing can go away. The whole thing is 1.
Okay.
Reaction order is 1. Okay. I also want to find out about A, so I can say 1 to 3, it doubles, and 1 to 3 stays the same. That's great. So now I can compare 1 to 3 and what happens to it.
4 times?
Quadruples. So what's its reaction order?
Second?
So N is 2. And that's my rate law for this reaction. Now I can say, what's K? What would I do? Take
Divide
anyone,
by
right?
4?
But what if, okay, so what if I ultimately want to define this? Which it looks like probably that's what I want to find since there are question marks there.
You have to find out K so that you can use K and the rate to solve for
Absolutely,
K.
absolutely. So any of the first 3 I could use to solve for K, because K is going to be same for all 4. Okay, so we could use the first one, we could solve for K, so the rate over the concentration of A squared is going to equal to K. So I would put in 4.0 times 10 to the minus 5, and A, 0.1 squared. Right, so let's see, what was the rate there? Let's see, 4.0 times 10 to the minus 5 divided by 0.1 squared. So what is that, 0.01? And sig figs 001, is that right? 0.1 squared is 0.01.
Yeah.
That should be pretty straightforward. And then 4.0 times 10 to the minus 5 divided by 0.01, what would that give me? 4.0 times 10 to the minus 3.
Yeah.
Okay. The rate itself over here, this is molar per second. And what do I have here? A is molar squared. So once again, this is going to end up in mole to the minus 1, second to the minus 1. And that should be my K. Now, I could look at this again. I could plug this in here. And I go to the fourth experiment. I plug in the 0.05 here. So this would be 0.05. And now I could solve for the rate here. Did everybody see that?
Yeah.
Okay, go ahead. Yeah, I'll walk you through. First, I kind of wanted to give you the idea of what's going on. And so you're thinking about it while I'm doing it. And now I'll just walk you through the slides. Okay, so determine the rate law for this. Calculate the rate constant, and then so that's everything we already did. By the way, you notice on exams this works a lot too. I ask you for this, then this, and each one leads you to the other one.
Yeah.
Right? So if you were to try to solve for this before you solve for that, you probably would have some complications.
Right.
Right? So stick in order. A lot of times there's a reason for that order.
I was just suggesting, are you comfortable with lifting the screen so you have more room to write on the board?
I could if people want that.
Yeah.
Is this hard to see when I do this on the side here?
Yeah.
Yeah? Okay. I could do that. And then I just write over it, yeah. Okay. So for now, let's go through this. This is what we looked at. We saw the quadruple, made it second order. That doubled, that quadrupled, second order with respect to A. And this one was, surprised I didn't do this one first. That doubled, that's constant. Zero order with respect to B. I mean, I would have just gone like we did the first 1 and 2 and then 1 and 3, but whatever. So with respect to A, second order. With respect to B, zero order. There's our rate law, and that becomes 1, and there we go. So what's the overall order of the reaction?
2.
2. Just 2. That's right. Calculate the rate of experiment 1. So once again, you could have used experiment 1, 2, or 3 for this. Doesn't matter which one you use. 1 is just the most convenient. It's the first one. That's all. Here are the numbers for it. So this was 0.100. The rate is 4.0 times 10 to the minus 5. Did we get that right? Here and here. This is that doubled. Here's our equation for K. Here's what we put in. This one's already done. And then we end up with this. Do we get it right? Yeah. There we go. So that's our K. So any questions on that up to now? Especially for those that maybe had a hard time seeing the sideboard here, which is probably why that question was asked. Go ahead.
Just something you got the n minus 1 and the s minus 1 or something.
So here, this is meter, or I'm sorry, molarity over second, so that's on the bottom. This is molarity squared. One of the molarities cancel with this one, which leaves the molarity on the bottom. So that's the same thing as m to the minus 1. This second is on the bottom, so that's second to the minus 1. And that's what I get here. Okay. So now let's move on and let's calculate the rate of the reaction for experiment 4. We already know K. We look at whatever the concentration of A is from the experimental data, which is 0.050. We know we're trying to determine the rate, so we just literally put it into the rate law. In this case, you can see that the molarity on here is squared. This is molarity on the bottom, so one of those cancel with one of these, leaving me with molarity, and still the second to the minus 1 on the bottom. That's how we unit it. Which is what you would expect, right? That's molarity per second, which is a rate. Okay. This times this squared gives me this. So that would be the rate of the fourth experiment. Now, what do we generally want to do? Does that make sense? Let's look at this number in the context of all of it, right? So you generally want to know, did I put in something that makes sense? So was there a pattern? Was it going down, or was it the same all the way through? And it should have been going down, so this is 1 times 10 to the minus 5.
Yeah.
Okay. 4 times 10 to the minus 5, 16 times 10 to the minus 5. Is this greater or less than this?
Greater.
16 is greater than 4.
Okay, and then it goes to?
A lower number because the concentration is low.
And as the concentration goes down,
The number should go down.
the number went down. Here the concentration went up, it went up, so it makes sense. Right? And that's the kind of thing you want to always go back and take a look at. Does my answer make sense and fit into what I would expect from the data? You don't know what that number is, but you should know whether it should go up or down. Right? And in this case, it went down. The reason, if it went up at this point, then you might say, wait, why? That doesn't make sense. What did I do wrong? All right. That's especially important, obviously, when you're doing independent research. Let's say if you're doing grad work or whatever, and you're putting things on, you don't just blindly put in the numbers because you solved it. Make sure that they make sense. Make sure that you're going in, and if they don't, make sure you could explain why. Because that might be valuable information. Wait, this didn't go what I expected it to do. Okay, my hypothesis was wrong. What does this mean? Maybe you have to now devise some new tests to figure out what it means because you weren't expecting that, which actually could be very good to your career because you might find something novel that nobody else knew.
Mm-hmm.
Right? But you got to make sure it's right because that is not good for your career. But you want to keep all these things in mind because just because you're learning it here and it's supposed to go a particular way does not mean it's going to go that way when you're actually doing research. And that's really the overall learning experience that you should be getting.
Can you go to the left side really quickly?
Which
The last one there. Yeah, that one.
Okay, so how are we feeling with rate laws, rates? How to put them together, how to solve for them, what they mean, what you need.
Pretty cool.
So far, okay?
Gonna get to K.
Okay, not yet. We got a few other things. Do we have another experiment here? So here, okay, the reaction below was experimentally. So here we're telling you the order. Okay, so determined to be first order with respect to O2, second order with respect to NO. Okay. Okay, so I like these questions. These are good SLO style questions, right? Because this is looking at something and not using necessarily quantitative analysis to determine it. Here you're just looking at your intellectual understanding of the concept and then trying to apply it, right? So here, I'm saying this is the red connectors here are O2s, and this must be the NOs for the nitric oxides, okay? Monoxide. Now, it's telling you that the first order with respect to O2 here, and its second order with respect to NO. And then it's saying which mixture in the diagram below has the fastest initial rate. So if it's first order with respect to O2, what does that mean?
It's double.
The rate is what?
2.
The initial rate is doubling.
Right.
So here I'm doubling, 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 doubling. What about the nitric monoxide? Quadrupling. So I'm quadrupling 3 times, 2 times, and 4 times. Which one has the fastest initial rate? C. That should be pretty obvious. Might not be so obvious, though, if you're on an exam and I'm not sitting here guiding you through that process. So remember that. For those of you that have had me know this, right? It seems sometimes a lot more simple because I already know it and I'm guiding you to what you should be thinking about. But on an exam, even though I'd like to, I can't do that because that's where I get to assess you and what you understood from them. But these are the types of questions. This would be a nice multiple choice question.
When you were doing the whole doubling, going on each one, what were you looking for again?
When I'm doubling the initial concentration of one of the reactants, right, or catalyst, and I'm holding everything else constant, I'm looking at what happens to the rate. As a result of what happens to the rate will dictate the order with respect to that reactant. And that's just the exponent.
Okay, yeah, the order. True.
And that's the
Yeah,
order.
Right.
Yeah. Terminology, yes. By the way, just to keep this in mind, I usually will allow you to have a sheet of paper or something that you could write your own notes on. So, putting things like maybe that chart will help, so that but obviously you can only put so much on that page, and I wouldn't over put on it, but, I would put enough on it so that you don't have to necessarily memorize things. Because, if you're in a lab and you're trying to figure this stuff out, you're not necessarily having to memorize any of this. You just have to know how it works and have a chart and use it, right? But if you can't use that chart, then it doesn't matter how much extra information you have.
Yeah.
So you got to make sure you know how to do it. I just don't care. I don't think it's necessary that you need to memorize it.
Okay.
Another example. Okay. The graph below shows a plot, reaction rate versus, so here's the rate versus concentration, and you see this linear line going up. Okay. What order is it with respect to this line?
One.
One.
Yeah, first.
As one thing doubles, the other thing double. How do you know that? So if I took the slope of this, I said, let's see, if I go from 0.06 down to 0.2, final minus initial, what do I get in here? What's the difference?
Yeah, 3.
Okay,
4.
so I come across here and I come down, I get 0.2, and I come across here and I come down, I get 0.6. And I double one, I double the other.
Okay, yeah.
If I double this, what happens to the rate?
Right.
That would be another way to look at it, which is exactly what we just learned, right? So maybe I should.
Simply from 0 to 2.
If I go from here to here, I double it, but usually you want to be in a better part of the curve, so this should be pretty obvious. If I take 2 and I double it to 4,
2.
I end up at 0.02 for the rate to 0.04. Did the rate double?
Yes.
Yes, so it's a first order.
Yeah.
Right, and this is very similar to what you saw before. If I wanted to make sure I had something right, so let's say, what if I started here at 0.3?
Mm-hmm.
What am I looking at this way?
At 0.5.
0.6, I'm doubling it.
Okay.
Right, so if I go 0.3 here, then I'm looking at 0.6. So if I go from here to here, I get what's that, 0.003, and over here I get 0.006. It doubles.
Okay.
Doesn't matter where I go on it, it doubles. That's what makes it a first order reaction. Does that make sense? Everybody see that? And that's all the question's asking there.
Yeah, from 4 to 8, or from 6 to 12. Okay.
Right. But you have to make sure you double if you're looking at the rate. Right?
Right.
And that's doubling this, seeing the rate.
Can you go back to example 3? Can you re-explain it?
So if I double this one, what happens to the rate? This is a first order, it tells you.
Doubles.
Oh.
It doubles.
It doubles.
If I double this one, what happens?
It stays the same?
Quadruples, it's second order.
Okay.
So then I want the one that has more of these, which are 4, because it quadruples it, as opposed to doubling it, the rate, because it's asking which mixture in the diagram below has the fastest initial rate. So the one that quadruples is going to be faster than the one that doubles. So where you have more that are quadrupling, 4 of them versus 2 and 3, that's going to be the fastest rate.
So basically the one that produces the most?
The fastest rate.
Yeah.
So produces meaning makes more product, I guess is what
Yeah.
you mean. Yes, but we're really looking at that is true, that's what happens, but we're really looking at the speed that it moves through in terms of the rate, right? But a result of that is what you're saying, yes. I just wouldn't think about it in terms of kinetics.
Would I be right if the way I thought about it when you explained it afterwards would be that I actually added the rate. So I did 1, 1, 1, I got 3 plus 6, I got 9 versus the 10, that one is actually greater than the A. You know what I mean? You know when you do the overall rate?
Yeah, but
order?
it's not like, so just keep in mind, I think I know what you're saying.
Uh-huh.
It's not like you're taking this one and quadrupling, then this one quadrupling.
No, I'm
So,
actually
yeah,
doing
right.
2.
As long as
so-
you're not doing that, then you're right.
Yeah, no, I did
Yeah.
2, 2, 2, I got 8, and then plus 2, that would be 10, a total overall,
You can kind of do that,
right?
right? You can kind of, but kind of not, because, once again,
See, that's what I was
if I
trying
have
to
3
do. Is
here,
that what you're saying?
Right.
and I have 4 here, and I have 2 there, all I'm saying is I double the so if I go from here to here,
Uh-huh.
which is doubling the concentration, or from here to here,
Right.
then I just double it. Here I have 2 to 4, I go from here to here, I quadruple. Which one's gonna have more? The quadruple.
Right,
It's
the
gonna have more than the
quadruple.
double.
Definitely.
It's not an addition thing. Right? It's the speed that the reaction is going to move is going to quadruple
Right.
versus double.
Correct.
That's what matters more. Okay, let's move on. Where are we at? Okay, now we're going to transition from the rate law to what's called the integrated rate law. So going back, what was the rate laws? Why did we look at the rate law? What was the major component? And I mentioned this earlier to start the class to make sure we were all on the same page.
For the
It
concentration?
was the rate with respect to
Concentration?
the reactant concentrations, right? So the integrated rate law, we're still looking at the rate law of a reaction. However, we also have to be concerned with what?
Catalyst?
Time.
Oh.
So the rate laws discussed earlier are the concentration of the reactant and the reaction rate. But we also can care, depending on what we're looking at, we can care about the concentration of the reactant and the time as well. So now we're going to do a couple little calculus calculations, and we're going to convert the rate law into the integrated rate law, but I'm not going to hold you responsible for that derivation. All I care about is you know it and then how to work with it. Okay? So you're not going to have to, I know that, I mean, I can't actually have you do that because I think the prerequisite is not Calc 1, right? So even though some of you may have had it, I'm not holding you responsible for how to get it. I'm just going to show you a couple things and a couple other mathematical things along the way to make sure you use it properly. Okay? So the main function here is going from the rate law, which is discussing the concentration of the reactant relative to the reaction rate, to the integrated rate law, which discusses the rate relative to the concentration of the reactant and the time that it takes for that rate to occur. Okay? So those are the distinctions. I'm adding on time, which is creating what I'm calling the integrated rate law. So starting with something,
So you can use it to like calculate the concentration at any given time?
yes.
Okay.
It's exactly what you're going to do. You're going to look at a particular rate, and you'll be able to determine, if you know the order, the type of rate, the integrated rate law, what it looks like, and therefore, as a result, at any given time, you could figure out what the initial concentration is. If you know the initial concentration and the final, you could figure out how long it took or some interconnection between those things. So you're looking at the initial rate to some time frame concentration relative to that time it took. So of course we're going to look at half-lives, and that's half of the time it took. That's half the concentration relative to the time it took to do that, to get half that concentration. And once again, we're talking about concentration. This is something to keep in mind, and I say it over and over and over to make sure that you're clear. We're talking about the reaction, the reactants concentration, not the product when we're dealing with these laws. Okay, it's really, really, remember, we started just looking at what rates were, and in just looking at a rate, you could place that into the product by seeing how much product is formed. But in the rate laws, we're only talking about the concentration of the reactants in the context of the rates. Okay, so here's a simple reaction. This looks like probably a decomposition. I have A is the coefficient, A is the reactant, and it breaks down into products. Only one reactant, that's why this is easy. Of course, we'll have multiple reactants later on. And here I have the reaction rate of this, if you remember, is just negative delta concentration of A over delta T. That became that. Now that should look pretty easy at this point, right? That's just the rate. Which also in the rate law equals K times the concentration of A. No big deal, right? All I did was I said, okay, if I had the rate and I looked at something like that, I know that equals to this over it's A and delta T. But I also know that that equals your K A, and we'll assume that this is first order, and we'll just leave that as is. We don't necessarily know that at this point, but we'll assume that. Or did it tell us that we were going to look at a first order? Maybe it just told. It would have to tell you that, otherwise you would have to solve for what this is. I'm telling you now, for the purposes of this, I'm going to say this is 1. So this equals this, which is all I have here. Nothing new there, I just combined a couple things. Everybody okay with that? Okay. This is the differential rate law. Differential for derivatives, that's the calculus part of it. Yep, okay. Now, if I move this A over here, I move the delta T up here. So now here's my time. Here's the A coming down here. This is now A concentration at a particular time given here. And this is the 0 means the initial A concentration. And I take the log ln of that. Okay, now this is where the calculus part comes in. So once again, you're not responsible for this derivation. Just kind of giving you a sense of what it's going to. Whoops. Okay, so then they want to stop there and they want to do something with that. They don't want to go further with this?
No, no, it's like that.
It stops there? Okay. Okay, so then we'll further this in a little bit. Okay, so here, this would be a first order. By the way, first order, second order, and 0 order are the ones we're going to focus on. 0 order is not as big of a deal. So I'm really going to walk you through a first and a second order, most likely. And then I'm going to give you a wrap-up of the rate laws and the integrated rate laws based on the order of something. And then I'll give you a little discussion on 0 in that mop-up, so you have some sense of it. I don't think they show it to you in the text. Okay, so here's a reaction. Sulfuryl chloride decomposes to sulfur dioxide and chlorine gas. In an experiment, the initial concentration of the reactant was 0.0248 molar. The rate constant is 2.2 times 10 to the minus 5 per second. The reaction order is 1. Okay, what is the concentration after 2.5 hours? Okay, now, a lot of things are given here. And the weird part about this is, as I walk you through it, I'm giving you certain things where later on, you're solving for those things, right? Just like we started initially, I told you what order it was, then we determined how to solve it.
Right.
So you could imagine on the exam, it's going to be more focused on you having to solve it as opposed to it being given. That's the first thing. Now here, when you looked at the rate law questions, remember on an exam, all the questions are juxtaposed, right? The first thing you should notice is that was a concentration relative to the rate.
Right.
Here, I'm giving you what? I'm talking about time. That should instantly raise an alarm in your head and say, okay, I need to work with the integrated rate law here, not the rate law. Okay, because I'm now dealing with time and concentration relative to the rate. Okay.
For the time, is it still going to be in seconds?
The time will usually be in seconds. In all fairness, it depends on what the rate is. So the rate unit should be, the time should be given in the rate unit because you have to cancel out units in order to get the proper concentration. So is the rate given here, the rate constant's given here as per second. The time here is given in hours. So in order to make this work in that equation, I'm going to have to convert this to seconds, but we haven't got there yet. But the units have to match. So if the unit was an hour, then you wouldn't have to change it, right, in terms of the constant. Okay. So what I want to develop here, though, is we have an integrated rate law. We're dealing with time and concentration relative to the rate, so I'm dealing with the integrated rate law here. And I know that because it says, what is the concentration of this after 2.5 hours? That's the time component of it. The other thing I know is I have an initial concentration, and now I want to know what the concentration is after the reaction is gone for 2.5 hours. So in the integrated rate law, let's go back, you have the time of, at some time, in this case 2.5 hours, what this concentration is, but you also have the initial concentration in there. You don't have that in the rate laws, right? So you're not worried about the initial and the final, or some particular time. But in the integrated rate law, it allows you to correlate the concentration initial, the concentration at some time frame, and that's the time given here. So then I just simply use this to solve for it.
So I know in this example, I gave it as a first order, and so for the first part, for the derivative
Hold on. I think I know. In the rate laws, when we found the order, we were able to figure out the order by just simply looking at that rate law and putting the exponent. In the order for the integrated rate law, it's not the same thing. So you're gonna have an equation for the first order, and you're gonna have an equation for the second
So there's
order.
different equations.
And they're different equations. And that's why I want to avoid your confusion. I know, I'm pretty sure that's what you're getting at.
Yes.
So that's why I took the first order here, did its derivative here,
Right.
which I didn't explain completely because you don't have calculus, you don't need to derive it. You just need to know it. Okay? When I do the second order, I'll take the second order and then I'll do some other thing to it, and then you'll have a different integrated rate law for the second, which is different than what you would have here, where here you know it's 1 because there's only a 1 there. Okay, but down here it doesn't translate the same. Okay? It only translates to what this looks like as a result of what that was. That make sense? Everybody okay with that? Everybody? Okay. Okay, so I have my initial, so that's the concentration of A, 0. I have the rate, and I have the time. So I have the time, I have the rate constant, I have this, so I'm solving for this. Everybody see that? Okay. So let's take a look. There's my A node, there's my K, and of course I'm going to convert that because the K was given in per second, so I need those to cancel out. And I'm solving for this. I know it's a first order. Now, if I didn't know it was a first order, I might have to solve for that if I had the data for it. Okay, so there's the equation. And I put all this in, and I get this times this. There's my seconds canceling. That's going to give me some number. It's negative here. So then I have this relative to this, and then I take the inverse of the natural log. That's the e to the minus something, right? On your calculator, usually it's second and then log. So you, depending on the calculator, you either put the second feature, natural log, whatever the number is. In this case, it's just going to cancel itself out, so you'll be left with this, and then you'll do that with this number, and you have to include the negative there. So most of you will put negative, you'll put 0.198 with the negative, and then you'll put second for the natural log, which is the anti-log, and that will give you a number. Whoops. There's the anti-log of both sides. So that gets rid of the log here, and it gives you this, which then gives you a number. So what I want you to do now is pull out the calculator you're going to use on an exam and make sure that this translates to this by doing that, because sometimes it's not so easy, and each calculator is different depending on a Texas Instrument and the year of it, and a Casio-based calculator.
Yeah.
Got it?
22 of them. Keep it in a 2 sig figs.
I'll
Okay.
discuss the sig figs in a second. Everybody get it? Anybody not get it, I should
Where's your
say.
E?
If you don't get it, then make sure you come to me and I'll figure out your calculator with you, and that way you'll be able to do
There
it,
you go.
okay?
And then
That's really, really important to be able
negative.
to do this. Because you might get it, you might do it right and then get the wrong answer, and if it's a
Right.
mess on an exam, I don't understand what you're trying to do, and I don't know it's just a calculator problem, I'll take off more points, right?
cool.
Okay. So now, then I just simply take this, I multiply by this, I'm multiplying up, and I get my concentration of A at 2.5 hours with the rate constant that I had. So it's just this, and that gives me 2.0 times 10 to the minus 2 molar, and of course, if it's a concentration, I should expect it to end in molarity. Right, so if I don't get that unit, I have issues.
For on the test, do you want us to write it in scientific notation, or is 0.0205?
Doesn't matter. Yeah, either's okay. Okay. Now let's do quick sig fig with logarithms. So if I have this here, and I want to know that this is now looking at log to the base 10, and I'll discuss that distinction between natural log to the base 10 in a little bit. But if I look here at this number, this is just scientific notation, right? And how many sig figs are in that? Two.
Two.
Okay. And I know that because only whatever I have in my coefficient, those are the proper number of sig figs, or they should be. What are sig figs again?
They show you the accuracy of your calculation.
Precision
The
of your measured numbers, right? Precision, what's the difference precision and accuracy?
Precision is like, it's gonna be everywhere, but the
Accuracy
same.
is how close it is to an external standard.
Accuracy, that's the easiest way to do it right there. Accuracy is closest to an external standard. Precision, numbers collective or further from the decimal, right, is more precise. Okay. Now, if I have 2 here and I take the log, natural or log to the base 10 of it, then I have to have 2 sig figs to the right of the decimal. It doesn't matter if I have 3 to the left, 2 to the left, 1 to the left, but I have to have 2 to the right of the decimal to represent these 2. Okay, and I think I did do something like that before, right? So 2 sig figs. If I do this with the log, I end up with negative 11.44. I put the 44 because these are the 2 that are representing these 2 sig figs. These are not representing sig figs. So then if I went the other way, then I would know that I have only 2 sig figs. That's how many I should have here. So the sig fig count in the scientific notation should be obvious. That's just the coefficient. Then to calculate the sig figs after you do a logarithmic calculation, it's 2 positions to the right of the decimal. If you had 2 sig figs, 3 to the right with 3, 1 to the right with 1. It's whatever number of sig figs you had in the coefficient now is the number of sig figs you have to the right of the decimal after the logarithmic calculation. No problem. And then, of course, inversely, you just look at these, the number of these, to determine this if you're going the anti-log direction. So that should answer your question, right? I think you started to talk about.
Yeah.
Okay, so let's do a couple more examples here. Cyclobutane decomposes when heated to this. And so here I'm telling you the reaction is first order. The initial concentration of the reactant is 0.00150 molar. I heat it to 450 degrees Celsius for 455 seconds, and the concentration was reduced to 0.00119 mole. So based on this, determine the rate constant for the reaction at this temperature. And by the way, at some point, that temperature is going to matter. That temperature is actually wrapped up, as I told you before, in the K. So at some point, we'll start figuring that out too. But for now, we'll just clump it together, and that temperature doesn't really matter for you in this context here, but it will matter later in how you calculate things. So that's given, this is given, and now I need the rate constant. Let's see, that was odd. Okay, so here's my integrated rate law for a first order reaction. I'm using that because I'm looking at the time relative to the concentrations at 2 different concentrations, my initial concentration and my concentration at the time given. So in doing that, can I fill in everything? What am I actually looking for here? K. I'm looking for the rate constant. One of the things I do, go home, write in rate of reaction, first order, second order, 0 order. Those are the main ones. The integrated rate laws for each one. Okay. And then what each thing means in it. Rate constant is the K. When you hear that or read that term, that should instantly come up that I'm looking for K. Okay? Here at 0, I had a concentration. At 455, I had a concentration. I'm looking for K. Do I know T?
Yes.
Yes, what is T?
455.
Whatever is written right there, right?
Right.
455, because at that time, that's what I'm looking for, what is the concentration. That's how they're correlating the time to the concentration relative to the order of the reaction. And here that means the rate constant is going to dictate the rate of it.
The temperature won't affect it at all?
The temperature will only affect it in relation to K, which you can't solve for yet. The temperature is actually wrapped up in K. So it absolutely affects it, but you don't know anything about it at this point other than it's just K. It's part of the constant.
Okay.
It will matter in about 2 lectures, or maybe even 1, depending on how fast we get through. But for now, I'm excluding it and just telling you it's part of K. And since k is a constant, that means I could wrap it all up into, a bunch of things are wrapped up into that k, right? Usually up to this point in most classes, k just means a constant. It is what it is. We're going to actually learn what k means in this class, in at least the context of a reaction rate and of equilibrium. We're going to actually have a definition of where these numbers are coming from. Okay, so here, I just put that in, right? Anybody uncertain about where any of this came from? Why am I using this equation? How did I determine this? Well, I'm on an exam. Why did I pick this equation?
Because you were giving time.
Given time, right?
I'm using time with concentrations in terms of the rate, and I'm using what order? First order, so I'm using this equation. Okay, make sure that everybody's on page of where these things are coming from. This is where it gets confusing, by the way. Even if this makes sense, all of a sudden you go home and you're like, wait, what do I do here? which equation am I using? Why am I using it? If you keep all these things in the proper context, you'll know exactly what to use, when to use it, and why you're using it. And it will make more sense as the more you use it. So I'm just solving for k there, so I must take, so here's, this is easy, right? I could just take this divided by this and take the natural log. Right, I don't have to do the anti-log here. And then I divide by a negative 455. So that just gives me this, which gives me that, and then I get this, and I get that, and then I divide, negative is positive, and my k comes out to be 5.09 times 10 to the minus 4th per second. Okay, so molar here cancel. I'm only left with the second here, but as I get down here, there's no concentration given here. I still have 455 second. I move the 455 down here. That's where I get the second to the minus 1, and that's what my k is. If you remember, first day of class maybe, second day, I think it was first day of class, we talked about k and what the units are, and it depended on what order of the reaction it was, even though we didn't know what order it was. So I just said depended on certain conditions, that's the order that will dictate k, the units that are used for k. Is this okay? No big deal? That's good. Okay. Okay, half-lives. That usually matters. Half-life, so that's just half-life. If you look, I'm going to suggest go back and read this a couple times for each of the major things that I point out, just to remind you of what each one means, because sometimes the meaning gets lost a little bit. So half-life is really just the time it takes for the reactant concentration to go down or to decrease in half, and what time that is. The confusion there, sometimes people get confused, is am I talking about taking half the time? No, you're talking about taking half the concentration. Okay, so if I started with 5 molar, I'm now looking at 2.5 molar. Half-lives in general just take on a particular form that makes it easier to work with if you're looking for it. It also, in general, in science, if you're working in a wet lab, you're working with radioactivity, and you care about what the half-life of that radioactivity is, because the faster it is, the quicker it will go away and you're not exposed to anything, right? So you have to know how long to store it for example. So by knowing what the half-life is tells you, how safe or unsafe you are in a certain proximity, or how to store it depending, I-131, P32, all kinds of things like that. And you use those regularly when you're trying to do a transcription and you're trying to make an RNA. How do you determine that P32? When you make probes to look at DNA protein binding, you use P32. So you use it for a lot of things in a laboratory. So ideally, its half-life is very short. The longer it is, that means that it's radioactive for that long. So if I have the concentration of, let's say, 500 molar, and it takes me 12 years before its half-life, then it's going to be sitting around a long time. I got to make sure it's sequestered in a way that it's not affecting anybody or anything, right? So that's usually why half-lives, that's the most relevant part of half-life. So for here, we're just going to learn how to put this in context. So if I'm looking at a first order, so I have this equation for the integrated rate law, and I want the half-life, that just means T1 half. What's the correlation between these? Half of this should equal that, right? Okay. There we go. Half of this equals that. Which is kind of nice, right? Because now, if I'm looking specifically for the half-life, what can I do? I could say, okay, I could just plug this in here, or I could plug this in here and with half, right? I could adjust. So if I want to just put this in here, what happens? 1/2 A over this. Can I combine those? They're now the same thing. Remember, the concentration of A at some time is different than the concentration of A initially. But now half the time, half the concentration of A initially divided by A initially, I could work with that, right? Okay. And that just, here I just put T1/2 because I'm looking at whatever this is relative to getting this. So if I do that, then I put all this together, I get, well, this is, so this here is equal to this. This here is equal to negative 0.693. Okay. So you don't have to derive it, that's just a given now. But you can, if you just want to put it together, you say 1/2, you know, A, and this is divided by A, and then you do what you would normally do in a mathematical operation. Then you do that, and then you take the log of that, you get negative 6.93. So it's just a given now. You don't have to calculate it or anything else. You're looking at the half-life for a first order reaction.
Okay.
You now know that the negative K, T1/2 is equal to minus 0.693. Ultimately, what are we trying to solve for here? T, the half-life, right? So if I divide by negative K here, I end up with positive 0.693 over K equals the half-life of a first order reaction. That should be interesting. Peter?
I'm just trying to figure out like what this would be used for. So like for radioactive isotopes or for like
If it's a first order reaction, degradation of something, it would be used for that, yes.
okay. What if it was
But a
like
first
second-
order,
What if it was like second order?
we'll get to that, we haven't got to that yet. You don't know the integrated rate law, so okay, let's keep this in context. Where are we at? Another question came up earlier about this. This is the integrated rate law for a first order reaction, right? What about a second order? Have we done it?
No.
No. That's a whole nother series of things that we're going to work on. This is just the integrated rate law for a first order, not a second order, not a 0 order, not a 1/2 order, right? And not a -1 order, even though we're not going to discuss a half or a -1. You only need to worry about the rate laws for those, not the integrated rate law. But for the integrated rate law, we've now converted the rate law of a first order into the integrated rate law, and that's what we're discussing now. We will discuss how to convert a rate law for a second order into an integrated rate law for the second order as well. We haven't got to that yet. Does that help?
Yeah.
Organization in your head is going to be complicated. There are a lot of things I'm throwing at you. So I'm trying to do it in the least intrusive way so that you can see the pattern of where we're at any given moment. Because at the end, you're going to have to be able to put it all together for whatever question you're being asked. Okay? First order. What's unique about, what's interesting about this half-life?
It's completely independent of the concentration.
It's completely independent of the concentration. In a first order reaction, it has no bearing what the concentration is in order to determine the half-life.
It all has to do with
It's only relative to K. That's kind of neat, right? So if I know K, or I know a graph and I could solve for K, then I could simply solve for the half-life.
I remember you saying before that temperature is
Wrapped up in K. It's all part of K.
So
When I take K, I'm going to unfold it into different things.
Okay.
One of those things is going to be temperature.
Right. So temperature influences half-life. So like if you
Well,
have
any temperature influences everything we've talked about in terms of rates. If you recall the very first day, one of the very first things I did, I talked about, I said, what kinds of things would influence the rate?
See where you get the point.
Temperature was one of them. I just haven't shown you where that influence comes from
How
yet,
we got that?
mathematically, and that's because but I have told you it's in K, I just haven't shown you
The A
how it
just
works yet.
cancel out.
Oh, okay.
So
So
you only
there
have one
are
half.
influences of like
Where's that?
isotope decay.
The negative is
Of what?
when you
Like
solve for it.
isotope decay basically. So
Mhm.
different like environmental
What the T equals.
factors could affect like
Well, let me
K
ask
we don't know
this,
yet.
it goes to your question. If I say K is a constant, which I've said many times, because that's why it's designated
So
K,
let's see where you got the point.
what does that, am I
693.
dealing with a change in temperature, or am I making an assumption in all these rates that the temperature is always the same? And anything else that's wrapped up in K is constant, which is why I'm able to throw it into that constant. That means when I'm making these evaluations of the rates based on the concentrations which are moving, and the times which are moving, everything else that's related to this is staying the same under those conditions, and that's why I'm able to wrap it all up in K. And we'll unpack K in after the integrated rate line. Okay. That help a little bit to like keep it in perspective where we're moving to and where these things actually are, so that yes, they do matter, but they don't matter in the context of what we're looking at here. Okay, so this is a given, so this is nice. Does not depend on concentration. Does that mean that the second order depends on, it doesn't depend on concentration? No, we don't know.
Right.
May or may not. The instinct, because of the way I asked it, is to say, no, that doesn't mean that, and of course it doesn't. But the good answer would be, I don't know, because you don't, unless you read ahead. Right, so keep that in mind. This is only first order reactions in the context of the integrated rate law, which was based off of a first order reaction rate law. Okay. That also means that the reaction does not change, the half-life does not change with time. Let me phrase that properly. So if it takes 10 hours for the concentration to be cut in half, then it takes 10 hours for that new concentration to be cut in half as well. That's what that means. That makes sense? It's kind of a tricky little tongue twister. Half-life does not change with time. That just means that the time it takes for each half-life is the same depending on where you're at. Okay. Oh, here it is. Concentration time. Starting at 1 molar, I cut 1 molar in half, so that means I go down to 50 to this point. That tells me it's 100 seconds. So then at 50 to cut it in half, it goes to 0.25. 0.25 over here, this is 200. So I went from 100 to 200, 100 seconds, half-life, the next half-life is 100 seconds, the next half-life is 100 seconds. So here I'm going 0.25 down to 12.5, etc. So that's what that other statement meant right here, right? The half-life does not change with time. The half-life stays the same because it's not concentration dependent.
Right. Just half.
Okay, so just put that in context. So at T0, this is after 1 half-life, after 2 half-lives, after 3 half-lives. All right, here we go. N2O5 decomposes. The rate law is first order because if I said anything else, we wouldn't know what to do with it yet. The rate constant of 6.2 times 10 to the minus 4th per minute. What is the half-life for this reaction? Do I need to now put this whole thing into the integrated rate law?
Right.
Can I?
Yeah.
What am I missing to do that? I don't know the concentrations.
Concentration, yeah.
But I could, right?
If you got the chart experiment.
I know it's half-life. I could just arbitrarily come up with any number I want and put it in as 1/2 that concentration divided by that concentration. And take the natural log of that, and it's going to give me what? Negative
693.
0.693.
Right.
So I don't have to do that. I can, because I could just come up with any concentration I want. It's just the same, right?
Yeah,
and that's going to give me the same number.
Exactly.
So I don't need to. I could just simply put the 0.693 divided by K. Because why? Do I have K? What is K called again? Rate constant. Make sure that term is familiar to you because it's new probably. This is the rate constant, so I put this over this. What's my unit going to be in? Minutes. Because I'm using minutes. Do I need to change that to second in this context? No. If it asked me to, I could. But it's not asking me to. Why would I? Right? If you were on a multiple choice and the answers were given in seconds, you absolutely have to because you're going to have different numbers. You follow that. That's tricky, right? if I gave A, B, C, D, and each one said seconds, and somehow I get an answer by putting this in terms of the minutes, it comes out with one of the seconds, you're gonna check mark and it's gonna be wrong, because it's asking per second, not per minute. So be careful on those kinds of things.
Oh, okay.
But if it was just a solved problem at the end, then I'm just solving it, I just leave it in minutes. But I gotta make sure I put minutes so that I know what you're talking about,
Gotcha.
right? If it had parentheses second, then I'd make that conversion. Okay, you can convert this, you can convert it at the end, wherever, it doesn't really matter. Of course, 60 seconds per minute, that's your conversion factor, no big deal. Okay, so this is 1,118 minutes. So is that right?
The -1.
How many sig figs should I have? 2 here, multiplying and dividing. So that should be 1100 or 1.1 times 10 to the third.
For the units for the rate constant, it's in, like, I know it's in minutes, which is fine, because you can go back to minutes and seconds, but there's no concentration. So when it goes from the integrated rate law to this new derivation that we have, is concentration changed so that K is changed?
K doesn't change here.
But the units are different, that's my only question. 'Cause
Units are different from what?
Because
Let me see what.
the units we used before included the concentration unit, so they were.
Are you,
molarity
which
and
equation are
seconds.
you referencing?
The integrated.
This one?
The integrated rate law.
Isn't that this?
Yeah.
Molar over molar cancels out. K and T. T is going to be given in something, and then you solve for K. So K in this case is still going to be seconds or some time, right?
Okay, so when the
Per-
molarity
per-
cancels out, it also cancels out the one. Okay.
I think you were asking about the concentration and the units associated with it. In this case, they cancel out, right?
So even
This
though-
is first order.
Yeah.
So in the
even-
first order, these are you're not changing any exponent in this equation here. So
Yeah.
you're always going to cancel the molar to the molar or whatever else you have. So you don't ever have anything with units of concentration related to the first order here.
Okay. So even though K before had a molarity concentration, it's canceled out from the other concentration.
Yeah, so one of the things I mentioned, if you recall, is that the unit of K is going to depend on the order of the reaction, right? And in the first order, in this context, K is just going to be a time. Oops. So where am I at here? What did we just do? This one, over here. By the way, what time does the class end?
2 minutes.
Oh, we still have, it
2
goes
minutes.
12:30 or 12:35?
25.
2 minutes.
25, okay. So let's try to get another example in here. Okay, so the first order reaction has a half-life of 26.4 seconds. Remember, it says first order. You got to make sure you read what that is. That's a really important piece of information. Don't get lost with that. So how long does it take for the concentration of the reactant to fall to 1/8 of its original value? Well, you know that each half-life is the same, so it's 2. 2 squared is 4. 2 cubed is 8. So there's your 1/8. So that's 3 times, right? That's 3 half-lives you're looking at. Okay. So if you have 3 half-lives, then what do I do here?
26.4 times 3.
$79.2 seconds. By the way, everybody agreed with what Taylor Ann said, right?
Yeah.
I'm assuming that you guys all heard that.
Scooby-Doo.
She answered the question, so I went on. That makes sense, right? Okay. Make sure I didn't lose anybody. I just realized that, I heard that and then I assumed everybody agreed with it. But if you disagree, please let me know, or if you see something different.
Disagree. No.
Can you say anything about the 3 half-lives again?
Oh,
You took the one-
so if I take 2, right, so a half-life, you're looking at taking half, and then you take half, and then if you cube the 2, it gets to 1/8, right? So that means I went half, 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 3. So then it's 3 times. So each half-life took the same amount of time, right? So each half-life took the 26.4 seconds, I identified there were 3 half-lives, so then I just multiplied 3 by those number of half-lives. That tells me it took 79.2 seconds to get to the 1/8 of the original value in terms of concentration. But that also, I mean, essentially that's the same thing as looking at this thing here. Right? So 1 half-life, 2 half-life, 3 half-lives. You see it half here, half there, half there. It came down from 1 to 0.5, 0.5 to 2.5, 2.5 to 0.125. That's the same concept. And then it took 1, 2, 3 times 100.
We wouldn't be asked as to
Which
like
would be 300. Huh?
we wouldn't be asked as to like 1/3, let's say. Like
Oh, no, you have to have something that follows the half-life
trend,
pattern.
right, okay.
Yeah.
Perfect.